Bismillahirrahmanirrahim. In today's lecture, we will learn about the details of a photovoltaic system. You already know that we generate electricity using the solar panels, right? So we are going to see how we make this electricity from the solar panel and how can we distribute them and on what principle the electricity is generated when it is stricken with the sunlight. Okay, now let us have a look what is a photovoltaic system. Uh, I believe you have seen on some of the roof in your area there are some photovoltaic panel, or in general we call them solar panels. So they convert the solar energy into electricity. There is a special kind of semiconductor material inside that will be excited when the sunlight strikes on it, and then it will produce current to flow, and we use that current to light up our homes and use the electricity from there. So this is generated in this photovoltaic array, if you see, right? And then it will go through, if you are using it for your individual home, that is stand-alone method. Stand-alone means you install your photovoltaic, you use it yourself only. You will have to set up a battery that will actually store the electricity generated, so you can use it later when the sun is not there in the sky. And you'll need a charge controller. This charge controller actually ensures that the battery receives the correct voltage and current from the PV panel. Okay, so it prevents the overcharging of the battery, because if you overcharge the battery, it will actually it will be actually damaged later on. It will shorten their life. So you use the charge controller in your house, and then you have to use something called inverter. Inverter is used to convert DC current to AC current, because by nature the photovoltaic will generate DC, but in our homes we use AC current, alternating current, so we have to use this inverter, and this is the setup for a stand-alone system. You can also have a grid connected if your area has a electricity supply system, central electricity supply system, or power development board. So what in that case you do not need the battery, because when you're running your home, after that the extra electricity will be going directly to the grid. Okay, in some countries like in Malaysia, what happens is when you install the solar panel, during office hour nobody is at home, so we are really not running the electricity like that. So during the daytime, the main power distribution board, we call it Tenaga Nasional Malaysia, so they will be receiving the electricity during daytime, and at the night time they will be selling back the electricity to the house from where the PV generated electricity was going. So those are all parts of grid connected system. So it can be directly grid connected, that can be a day and night balance like in Malaysia. Some more details about stand-alone PV system. Operate independently from the grid, require batteries for storage. Okay, and you can apply it in the remote areas where the central power distribution system is not there. It can be used in water pumping in farms, or it can be used on the sea for if you have to do anything pumping there, or any electric supply is needed, you can just install the solar panel there, right? And also like telecom towers, right? Telecom towers are usually established in those places where actually no man goes regularly and no electricity supply. So there you can actually set up this standalone photovoltaic system. So these are the detailed diagram that we have discussed previously. There's a PV array, and there is a way to understand whether it's a what type of PV is this by looking into the color. We will learn about this. You will see, if you observe the PV panels around you, you'll see either they're blue or black. Then this charge controller, battery, inverter, and then house. Okay, so this is the stand-alone PV system diagram. I may ask you in the exam, right, describe about the stand-alone PV system diagram with a sketch. So you have to draw it and then explain it a bit about all of these different categories of components description. Okay, next is the grid-tied photovoltaic system. It is the best choice when you are staying within an area where there is already some power distribution system available, like there is a central power distribution center. So in that case, you will get rid of the battery charges. You don't need the battery. Definitely the battery costs you a lot. Okay, battery is the most pricey element. It is even pricier than the photovoltaic itself. Okay, so battery is the most costly element, so you don't need the batteries for the grid tied, but you have to have a grid, right? And then if you are able to produce excess energy, then you can export to grid. Either you will get money in return, or you will get the electricity during night time, so you will get some extra cost off from your electricity bill. This is a hybrid photovoltaic system. Well, depending on the situation, it can run only for the standalone system, or if available, then it can also be grid connected. Definitely it provides more flexibility and higher reliability, but definitely its cost will be higher. Now it's a brief comparison between these three types that we have learned: standalone, grid-tied, and hybrid. So the standalone will operate independently and it will require battery storage. So the advantage is like you run your own system. Okay, you can run your own system, and as long as there is sunlight, you can run your system. So it's an excellent choice for areas where there is no central grid available. And disadvantage is definitely you have to face the consequence of having the battery maintenance by yourself. Okay, and the battery storage capacity is not very exciting. Okay, so that is one limitations. And typical application is for remote homes, telecom stations, water pumping. You can use it on a sea also, right? So you can use, I mean, wherever there is a remote area, you can use it. And the grid tied, we know already that it will cost us lower cost, and then we will have the excess power to sell to the grid or somehow get some advantage from the grid. High efficiency, but disadvantage is if your connection with the grid is not there, somehow disturbed, then you do not have any backup during the grid outage, right? You cannot store because you don't have the battery with you, right? So that is the one major disadvantage. So that means your connection with the grid must be very much secured. And its application is like residential areas, commercial buildings, utility scale photovoltaic systems. Okay, so and the hybrid is combined. That means it is checking all the possibilities, whether there is any interruption in grid connection, or like but you have to like consider the cost, right? It's a higher upfront cost, more complex design and maintenance, because you are serving both sides, both standalone and grid tied, but it's much more reliable in terms of advantage, right? And it can be used in hospitals, because hospitals are our critical service areas, right? Critical infrastructure, smart homes, microgrids. I really wish and hope that inshallah in Gaza's hospital this system will be later installed, inshallah. Now it is time to look in a greater detail into the photovoltaic process. We will see how this process takes place. So these arrays are created by connecting modules, because we understand that photovoltaic itself is a very small one. So there will be multiple photovoltaic cells in arrays to be connected and produce higher amount of power. So its efficiency, there is no moving part, nothing. It is just like constrained by the material. The material is exposed to the sun, the photon will strike the material, and then there will be a flow of electron. So the efficiency is quite low. So if you are using the crystalline type, you will have 11 to 17% efficiency, and the thin film, we will learn about thin film later, they will have 6 to 12% efficiency. Now we are going to look into details of the photovoltaic effect. So sunlight contains photons, is a tiny packets of energy, and the material that is used in the photovoltaic cell is kind of silicon doped with different materials, we will see later. And these photons will strike that semiconductor material, is usually based on silicon. And if the photon energy is higher than the band gap of a certain voltage, then it will excite an electron to the conduction band. This process leaves behind a hole because one electron is jumping out, so there is a positive charge carrier created. Together, the excited electron and the hole form an electron hole pair. So one is positive and one is negative. And a p-n junction. So p-n junction, we will learn about it later, is the solar cell. In the solar cell, it creates an internal electric field because it is gathering all the electron on one side and the hole on the other side. So this field separates charges. Electron will move to the n side, holes to the p side. And separation prevents the recombination of electron and holes together. So we connect it through an outer circuit, external circuit, so all the electrons will flow and producing direct current. The flow of charges through the load generates the usable electricity. In this video, we will see in details how the solar
Have you
photovoltaic
ever wondered
system
how a
works.
solar panel generates electricity? A solar panel consists of many solar cells, each made up of multiple layers. The top glass sheet protects the cell while allowing sunlight to pass through. Beneath it, an anti-reflection coating prevents light from escaping. Below this, a thin N-type layer contains free electrons, while a thicker P-type layer holds holes. At their junction, a depletion region forms, with positive charges on the N side and negative charges on the P side. When sunlight hits the depletion region, photons excite electrons, freeing them from neutral atoms. These electrons move toward the N-type layer, while holes move to the P-type layer, creating a flow of current. To collect and transport this current, metal contacts are placed below the P-type layer, while thin metal strips run across the top of the cell. This generated electricity can then be used for power.
Okay, we have seen that the semiconductor material inside the photovoltaic cell is silicon, but silicon is available readily in the nature. But does all silicon produce electricity? No, we have to do some engineering to this semiconductor material silicon to create a p-n junction. So on the p-n junction, uh, one is doped with phosphorus on the n, and the P is doped with boron. So when you are doping the N type, N side, it will create extra electrons. It will provide extra electrons, and on the other side, the atom that create holes in the P type, the boron doped side. So this junction creates already a built-in electric field. Now, to activate this electric field, the sunlight photon will hit the semiconductor and it will excite the electrons from the valence band to the conduction band. So, the creating electron hole pairs, the built-in electric field at the p-n junction pushes the electrons toward the n side and the holes toward the p side. Okay. Now, there is a value after which there will be the flow of electrons start. That is, the right band gap is 1.1 EV for efficient absorption of sunlight. So when this value has reached, then the electricity will start to flow. And why do we use this silicon base? Because it's not toxic, it's stable, it's available everywhere, and it's abundant in nature. So sand, you have seen the silicon dioxide in sand already. So that's why it has been prepared from the silicon based material as semiconductor. Now we are going to learn about the valence band and conduction band. So in a normal silicon crystal, each silicon atom is bonded to four neighbors. All the four valence electrons are used in these bonds. The interaction between silicon atom and their valence electron result in the electron energy in the crystal falling into two distinct energy bands. One is the valence band and one is the conduction band, and they are separated by the energy gap called the band gap. So there is no allowed electron energy in the band gap. Okay. Now we do the doping, and the doping introduces the p-type boron and n-type phosphorus. So this one will enable the electron flow and current generation. And the valence and the conduction band, I'm just reminding you there is a difference. The difference between them is valence is the highest range of energies where electrons are normally bound to the atoms. Okay, and conduction band is the range of energies where electrons are free to move, enabling electric current. Okay, between them there exists a band gap, so that's an energy barrier that actually separates the electron from start the flow between these valence and conduction band. Details about p-type and n-type. The p-type is created by doping with boron 3 valence electrons, and n-type is doped with phosphorus with 5 valence electrons. So together they form the p-n junction for PV operation. Now the electronic property of semiconductor, the band structure is the main thing here. So this band structure defines the energy level that an electron can have in semiconductor. And transport and optical properties are also determined by the band structure. Now we also trying to see like how do we modify this band structure, how do we do the doping, right? So we modify and optimize the devices by mixing of semiconductors, heterostructures, and then we do the doping and alter their free carrier density. So how many free electrons they can carry, that one will be determined by the doping. Before that we do the mixing of the proper semiconductors to obtain a heterostructure. Now let us have a look how does the current flow. Previously we have seen that there will be holes and electrons, but there is a gap also, the energy gap. So due to that, when we have like done all the doping and the photon energy is striking, and after striking it's actually creating more and more holes and the more and more free electrons, we will be getting the electricity. How do we do that? The depletion region with the diode is the area around the p-n junction. Okay, so we attach the diode around the p-n junction where the electrons from the n-type have diffused into the holes of the p-type material. So when the photon is absorbed by one of these atoms in the n-type silicon, it will dislodge electron, creating a free electron and a hole. The free electron and the hole has sufficient energy to jump out of the depletion zone if a wire is connected from the cathode. So that 1.1 eV barrier has been already exceeded. So now there is no problem for the electron to jump outside if you just connect the load with this. Okay, the load is here. So if a wire is connected from the cathode n-type to the anode p-type, okay, electrons will flow through the wire. The electron is attracted to the positive charge of the p-type, which is the anode material, and travels through the external load, creating a flow of electric current. So you can see that here is the location of anode and cathodes are there, so electron will be flowing through this and coming back. Okay, meanwhile we will be getting the current here. Now we will talk about energy band. Okay, so this energy band or the band gap, that is depending on the photon's energy. If the photon's energy is greater or equal to this band gap, only in that case the electron can get enough energy to jump from the valence band to the conduction band. Now how about looking into the efficiency of band gap? Okay, band gap and efficiency, how are they relevant? If the band gap is too big, too large, then what we understand generally is the most photons don't have enough energy to excite the electrons. Therefore, there will be low absorption, and if the band gap is too small, then there is a chance that the photons give electrons more energy than needed, so the excess will be lost as heat, which is a very common phenomena for photovoltaic. So the sweet spot, right, there should be a sweet spot maximizing the useful absorption while minimizing losses. So silicon's band gap has a value of 1.1 eV or 1.1 electron volt. Okay. So as long as this 1.1 EV is exceeded, then the electron will flow normally outside the solar cell through the circuit, and then this value matches well within the energy of many photons in the visible spectrum. So that's why we pick up silicon. Number one is very readily available in nature, plus the band gap is very much suitable to the photon that is coming to the earth from the sun. So it absorbs a large portion of sunlight efficiently, but theoretical maximum efficiency is up to 33% for single junction silicon cells. Okay, 33% maximum theoretical, but in practice we really do not go more than 20. Yeah, more than 20. Okay, enough of the solar cell, details of photovoltaic transition. Now we are going to see what type of solar cells are available in the market. So the one available, most commonly available if you want to look for the online purchase, will be monocrystalline, polycrystalline, thin film. So these are the monocrystalline and polycrystalline is readily available, and monocrystalline means there is only one single silicon crystal. Polycrystalline means they have multiple crystals. So monocrystalline is a high efficiency with a higher cost. Polycrystalline is moderately efficient with a lower cost, and thin film is like, it's not directly the silicon crystal, rather it is distributed over the carrier material. Okay? And there are some emerging technologies like perovskite is one of the most emerging one, solar cell, okay? CDTE, CIGS, but perovskite is making its way quickly into the PV business. Now quickly to check, right, if you have monocrystalline it will be black color, and polycrystalline will be blue color. So there is a quick comparison of the solar photovoltaic technologies. So you can see by the appearance, monocrystalline will look black color, rounded edges, okay, because it has been cut from the single crystal. While polycrystalline will be bluish color and it will have grainy surface because there are multiple crystals there. And thin film is thin, flexible, it can be black, dark brown or other colors. The material used for monocrystalline is single crystal silicon wafer. Polycrystalline is multicrystal silicon wafer. And thin film, it is having a layers of semiconductor. And this is deposited on a carrier material which is a glass, metal or plastic. So efficiency, monocrystalline is highest, polycrystalline is medium, and thin film is lower or lowest, you can say. Now in terms of cost, obviously the highest efficiency monocrystalline is the highest cost. Polycrystalline is medium cost, thin film is the cheapest. Besides, if you are talking about the land area required to produce the same amount of power, monocrystalline requires the smallest amount of area. Polycrystalline requires higher than monocrystalline, and thin film, since its efficiency is very low, it requires very high amount of area. Now we will look into the widely used terminology relevant to PV module. Okay, so you will be introduced to this IV and PV curves. So before we begin with this curve, I just want to let you know that there are two parameters. One is the ISC, short circuit current, and VOC, open circuit voltage. That means the maximum possible voltage when current is 0, and short circuit current is maximum current when voltage is 0. So if you want to see on the IV diagram here, so your ISC is the highest possible here with the 0 voltage, short circuit, and IV curve follows like this, and VOC, open circuit voltage, is the highest, right? So in between it works, and if you see the actual PV curve, it will go like this. The maxima is determined by the few key terms, which is maximum power point MPP and maximum power point tracking is the technology MPPT. So you can see the maximum power point will be required for the optimal operation, where power is the maximum. So VMP and IMP, where they coincide, this is the maximum power point we can get. Okay, MPP. Now the point where we get the maximum power is called the IMP and VMP for current and voltage respectively. So maximum power point tracking is the technology in the inverters controllers to keep the PV system operating at Pmax. Okay, you can have watch this details video of the in situ IV measurement in the following YouTube video link if you want. And now we talk about the open circuit voltage. So definition already mentioned in the previous slide, maximum voltage across the solar cell when no current flows. So it occurs when the output terminals are not connected to any load. So it has the highest potential open circuit voltage. And depending on material, 36 cell silicon module may have open circuit voltage from 20 to 22 volts. Okay, it is important to know what is the open circuit voltage, because you need to set the upper voltage limit for the PV module, like how much can the overall system take up. The short circuit current, when the current that flows when the PV module's terminals are short together. So that means the voltage is zero. It's the highest amount of current flow through the module can deliver. So if you have a look, what is the value? So for a typical module, it's between 5 to 10 ampere. Now it is important because it indicates the maximum current rating needed for the controllers and wiring, because wiring will get heated depending on the current's value, right? So you need to know that at what type of wiring is required to handle the maximum amount of short circuit current. So when we need to run the photovoltaic, we cannot go for open circuit voltage or short circuit current. So in that case, we need to know the maximum power point, and the maximum output power a PV module can provide is called the maximum power point. And then we track back at this maximum power point what is the voltage generated and what is the current. So depending on those values, we will call it voltage maximum point, voltage at maximum power point, and IMP, current at maximum power point. So it's located at the knee. Remember the IV curve, it has a knee like this, so it's located here. So if you read the ISC should be the highest, IMP is slightly lower than ISC. Similarly, the voltage, open circuit voltage is the highest, and the voltage for the maximum power point should be slightly lower than the open circuit voltage. So this axis is voltage and this axis is current. So this is the knee, right? So this is the point. So for example, a 250 watt module might have VMP is 30 volt, IMP 8.3 ampere. Important because the Pmax defines the module's rated power. Okay, so when you're purchasing, if you just search for online purchase of solar modules, so you'll see that the PMP and also IMP, VMP will be listed in the manual. Okay, so you need to know like whether I need to buy 100 watt, 50 watt, how many panels. So this one is the Pmax based on 100 watt, 50 watt, whatever wattage you want. Depending on that, you should have to choose your solar panel. Now we have a look into the efficiency of photovoltaic cell. So efficiency is always the ratio between the input, the output, right? So how much I'm getting and how much I have to supply to get what I'm getting. So the input here will be the sunlight coming from the sun, power in, and output we will look into the power max, Pmax MPP, maximum power. So it should be the ratio between the IMP and VMP. Remember that knee, right? That knee. But the overall solar irradiation is coming at watt per meter square. Remember, we have learned about this. A solar radiation is watt per meter square. So I need to involve the area for which I have the solar panel installed. So solar panel's area will be one factor because I am using the solar irradiation in watt per meter square. So multiplied by area in meter square will give me only watt, the incoming solar irradiation, and how much of it is converted to the power that I require will be IMP into VMP. Now if I don't want to write this expression as IMP or VMP, then I need to introduce a factor, the fill factor. The fill factor is the ratio between the IMP VMP over ISC VOC. Remember, ISC and VOC is the maximum possible current and voltage coming out of a photovoltaic cell, and it won't occur simultaneously. You cannot have maximum current when you are having maximum voltage. So if I want to replace the maximum possible IMP VMP at the maximum power point, then I take their ratio as a fill factor, then I can express the outgoing power, the generated power, as ISC VOC multiplied by FF, right? So eventually this and this will cancel out, so remaining will be again IMP VMP. So this one is a fill factor. This one is like commonly used for describing the efficiency of solar cell. Okay, let's have a quick look into the major equipment, right? We have focused on the photovoltaic cell itself. Now we have to look into the inverter, the types of inverters used, then the charge controller, and all those things, right? Just need to know like what are these things. So inverters are used to convert DC to AC power because by right the photovoltaic generates DC current, but all of our equipment used are running on AC, right? So inverter does the job. And then this one is mostly for standalone and also grid tied. Both cases you need to convert the DC to AC. Whether you're sending it to the grid or using yourself, you need to convert it. So inverter is a must in the PV system. Then it must meet the IEEE or universal standards, right? So inverters now you can just purchase along with the photovoltaic module as a package. Okay, now we are going to have a look into the conversion of inverter. So since it's converting from DC to AC, the simplest one is the square wave. I believe you have studied about this in your second or third year electrical engineering courses, right? So how do we convert from AC to DC, DC to AC? So from DC will be a straight line, and then we can go by like square, or we can go by like modified sine wave is like this, like small staircase pattern, and the pure sine wave is the most high quality, highly efficient, right? That's the usual one we have in our electric supply, right? And then we, for the efficiency improvement, we have to do the uh, wave modulation and also the maximum power point tracking, right? So we have to get, this one is the most efficient one. Now let's have a quick look at the batteries. Batteries is a must for your standalone system, right? You can actually go without the battery for the grid connected one, but for if you're running for a standalone, you have to store the energy somewhere to use at night or the cloudy days. So it is costly. First of all, battery is the one of the most expensive equipment. It's even more costly, that it can go even more costly than the photovoltaic cell itself, and it adds cost and maintenance requirement. And you know that there are different kinds of batteries that we're going to look into the next slide, depending on the battery material, right? That can be an environmental concern also. And recently there has been like huge research ongoing for the EV vehicle, electric vehicle, on the batteries. So we can later integrate all these research on battery into the photovoltaic for standalone. So battery types are like the lead acid, cheap, reliable but heavy. Then VRLA, that one is a gel battery. It's maintenance free, longer life. Then NICD is nickel cadmium, right? Durable, costly, but toxic. And lithium ion is an emerging one. It's high efficiency but still expensive. Now we will talk about the different categories of these batteries, right? We are going to compare these four types. So we will first look into where we are going to apply this, right? Based on the application, we should try to see, then we will compare between them. So we can see that typical application, rural electrification, small standalone PV system is suitable to go with lead acid because it is quite cheap, but it's heavier, right? And then if you are talking about the telecom backup, where you must have continuous flow of electricity, UPS, then medium scale photovoltaic, then going for the gel batteries are one good choice. So AGM means absorbent glass mat or gel electrolyte. So it's maintenance free, right? So it's a good one to set up for the telecom, because telecoms are usually set up at the high hills or some, all those areas where people do not reside there. So there's nobody to go and check every now and then for the quality. So you should pick up the maintenance free type, although it's a bit more costly, right? Then for aviation, okay, remote stations, really remote stations, industrial photovoltaic system, uh, or I'm not sure whether it can be used in the satellite also. So you should be using the nickel cadmium batteries, because first of all it's using toxic cadmium, so we don't want to use it in a densely populated area. But it has a long life cycle, right? So it's good that if I want to send satellite in the outer space where there is no human or no animal, so no issue of the toxicity, I can send it with the nickel cadmium battery system for my photovoltaic system inside the satellite or rocket, right? So but it's very expensive, by the way, but who cares when you're doing the satellite thingy, outer space is, everything is very expensive, okay? And lithium ion, this one is really picking up recently. You should study more about this because this one is really into the research now. Plenty of researchers are doing it for the lithium ion, even for the electric vehicle. So this one is modern high performance battery with high energy. So you can use it for residential photovoltaic, storage, microgrid, electric vehicles, right? But it still has the high upfront cost. But there has been intense research going on to lower the cost because it's lightweight, compact, right? And it also has a long life cycle. It's fast charging but low self-discharge. Now into the charge controllers. We have seen that after the photovoltaic cells, there is a charge controller that controls the fluctuations in current voltage to the battery, right? So this one is used to regulate the charging, discharging of batteries, prevent overcharge, deep discharge, and types are like whether it's a on off or pulse width modulation, PWM, or maximum power point tracking. So this one improves the system efficiency and battery life. There is a comparison among different types of charge controller. On-off type, a simple regulator, and its typical application is very small solar system. With solar lanterns, small off-grid lights. It's kind of inefficient. It wastes the potential energy and no fine control, right? Because when it's on off, there is definitely no fine control, but it has some advantage. It's very low cost and simple design, okay? And pulse width modulation is suitable for small to medium standalone photovoltaic system, rural electrification. It is more efficient than the on-off, but still like loses some power. And it regulates the charging by rapidly switching photovoltaic input on off, controlling average voltage to match battery charging needs. So that means it's not really very smooth one, right? Not really smooth one, just like on off, 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 like this. Okay, so we do the pulse width modulation. Then for the maximum power point tracking is the more complex and highest efficiency so far, up to 30% or more energy than pulse width modulation. It continuously tracks the PV module's maximum power point and adjusts the voltage current to extract maximum power. So it goes to the VMP and IMP, adjust it to get the PMP, the maximum power. Definitely is higher cost, more complex, and this one is suitable for medium to large photovoltaic system, or it can be used in the hybrid system, right? And grid tied plus battery storage, where we use the grid tied and battery storage. Now it's time to talk about the cost. The grid connection distance is one factor that affects the photovoltaic system cost, right? Because the further the grid is, the higher cost you have to bear. Then obviously solar resource availability. If your area doesn't have enough solar irradiation, then your PV cost will be higher, right? Because it cannot get the return on investment, or payback period will be longer. Then module type, what type of module are you using? Monocrystalline, polycrystalline, thin film, and efficiency, definitely what is the efficiency, plus installation, and then overhead and maintenance and incentive, right? So these are all affecting the photovoltaic costs. Then we are going to talk about the trends that is coming up in PV technology cost. Now, one good news is the PV module cost is declining steadily with the progress in material development, right? And now you know that there are foldable solar cells available also, so foldable, so you don't really have to like transport it in the rigid structure. Then inverter and bill of the system cost is reducing. Then thin film growth is increasing. They are now achieving higher efficiency, and the learning curve reduces cost with scale. So if you're scaling it up, you can actually get many customers. They're interested to install photovoltaic in their house, then your cost will be reduced. Now, efficiency improvement, what has been going on now? We can, if we have seen that thin film requires the highest amount of space because it's a less efficient. So if you have high efficiency photovoltaic system, we will have lesser space, but cost will increase. And space, you just cannot keep on wrapping the earth's surface with photovoltaic, because the amount of heat that will be wasted from there will increase the temperature in the area, plus you will be losing on the land suitable for agriculture also, because our human population is increasing, our food is now getting limited, we don't have enough land to cultivate. So you just cannot keep on putting up photovoltaic for energy, because you need to save the land for cultivation also, right? So you have to balance between this. That's why nowadays, you know what, they're utilizing the sea. So on the sea, they put in the floating solar cells. China is doing quite good in that. You can actually Google about it, the floating PV modules in China. Okay, so but if you make the system larger, it will reduce per watt cost. Okay, and then there are lots of innovations going on, like thin film, nanomaterials, perovskite. So there has been the improvement ongoing. Application of photovoltaic system: residential is rooftop, they install, then off-grid homes, commercial buildings, offices, industrial large-scale plants, remote operations. Building integrated PV or BIPV, I'm going to now talk about this in details. This one is photovoltaic integrated into the walls, roofs, windows. There is a special type of photovoltaic cell where you will have the windows, and it will reflect the light, guide the light to the window sills. And dual purpose is electricity and building material. So the building material, if you are making up of photovoltaic friendly things, then you can actually get in one thing you can get two: electricity and building material will produce the electricity for you. Reduces net cost of photovoltaic adoption if you are doing it for a large building. We're almost toward the end. I'd like to complete it with the challenges in photovoltaic system. So definitely installing has some cost, but we try to reduce it by calculating the payback period and also the return on investment. So based on the payback period and return on investment, it seems lucrative to people. Then we have the storage limitation. Where do we store? If we don't have battery, then I must be connected to the grid. Then if I have to be connected to the grid, then the grid integration and stability, right? And then what is the lifetime? Its average lifetime now is like 20 to 25 years. So after this 20 25 years, how do I do the recycling? Okay, do I just throw the whole system? Then it's going to be harmful for the environment. So we haven't been doing much on this side yet. Then available limited land space. This one is very much concerning. I need the power. I also need land to produce my food. So what to do? In some countries, what they do is they find out which type of crops or which type of plants they can grow under the shade of the photovoltaic, because under the shade of the photovoltaic there is heat but there is not direct light. So those type of cultivation, if they can do it underneath the photovoltaic area, then they still can use that area for producing that type of crop. So this type of research is ongoing now. And obviously people are using the sea to make the floating solar cells, but we don't know about the environmental impact yet, whether installing this thing over the sea will again harm the sea's natural balance or no. So these are the challenges upcoming, and definitely the low efficiency is the greatest challenge. Okay, so people are doing that one in terms of materials aspect. They are trying with different types of materials. So this is the future prospect. Like there is rapid growth ongoing, no worry, no wonder about that. But integration with the smart grids now are coming up. Different types of grid, like that is like small but can be connecting a few localities together, a few community. Then advances in this perovskite storage hybrid systems are ongoing. So these are the future prospects of photovoltaic system. Then summary, what we did is how photovoltaic converts sunlight into electricity. We have learned about that. Then we have learned about different types of photovoltaic systems, standalone, grid-tied, hybrid. And we have talked about the main components. Costs are falling, efficiency is improving, there is one hope. Applications expanding across all sectors. We have also talked about the challenges. Now, research and innovation opportunities in this topic, new materials, right? So if you want to, in future, you want to study in solar energy, there is scope for you to do the research on new material like perovskite, organic. Then how can we do the storage more improvised, improve storage integration, policy and incentive for adoption, like most of the countries, they will give the tax rebate if they are installing the photovoltaic in their house, so they will get some tax rebate. This is how it's getting like popular among the people to accept it. Then photovoltaic you can use also for water purifying, water desalination, or agriculture, right? Agriculture, you can use the photovoltaic for using the pumps, right, in the agriculture field. Sometimes you can use the heat that is generated under the photovoltaic panel to dry up the fruits or crops, okay? And also EVs, right? EV, this one is still in very much research stage. I haven't seen any car running with the photovoltaic panel yet, but this one can be one scope for the further research. Besides, you have to search on your own about particular issues. Yeah, we are more interested now to know that we know that photovoltaic is coming up, but there are some areas that is already saturated with the photovoltaic. Now, what are the environmental impact we are having? That is very important to know, because that one will guide us for the future direction in installing I just cannot keep on installing photovoltaic everywhere. I have to think about the land, the agriculture, cultivation, and also the all the animals and everything. I mean, overall the whole ecosystem, we have to look into the effect of photovoltaic, like installing photovoltaic. How much can we do by not harming, or at least do go for an optimized setup? That is all for this lecture. Thank you. Assalamu alaikum.